Good afternoon, everyone. Thank you for joining us at our first ever Inforce conference. I hope you've had an awesome 2 days learning all about AWS and about security in general. So in this session, we're going to talk about serverless security. And serverless is one of the hottest innovations in the cloud today. It's one of the most rapidly growing design patterns. So we're going to talk a little bit about the strategies that you can use to help secure some of your enterprise-grade serverless apps. So my name is George, and I'm a specialist solutions architect. I focus on the serverless portfolio at AWS, and I'm responsible for helping our customers build and operate serverless applications on the platform. In the past life, I was a software engineer, and I spent a lot of time building web applications. All of my contact information is down below, so feel free to reach out to us if you have any questions after today's talk. So here's our agenda for the next 45 minutes or so. This is going to be a fairly technical session. We're not going to do a lot of introduction. We're going to go over some tips and strategies and best practices that you can put into use into your applications today. So at the very end, we'll go over some common vulnerabilities and show you how this will affect some of your applications that you're building. So let's start with basic security principles. So the first principle that we have is related to this. Has anybody ever done this before? chmod 777, right? I think I've done this, everybody's done this. If you're not aware, this is basically a Linux command that says, give me any user, any group, full read, write, access, delete permissions to any file that you set it on. So this is not something that you typically would consider good security, right? The good news is that when you're building serverless applications, you let AWS handle a lot of the hard details about servers and operating systems and infrastructure. So you typically don't have to worry too much about file systems and operating systems and those kinds of things. So our first principle is least privilege. Right? Least privilege says we should only grant those permissions that are essential to perform your task or your operation. So if we take a look at this example here, on the left, I have an IAM policy that's allow DynamoDB:*. So in effect, this gives any user permissions to perform any IAM permission or action on a resource that's also a wildcard. So this is basically an admin permission that allows me to do anything I want to any table in the account. So least privilege, what we want to do is scope our IAM policies across the board. You should be scoping your policies down to only limiting the permissions that your applications need to perform. So on the right here is a better policy. This is scoped to allow a single DynamoDB permission. So that DynamoDB permission is put item. And further, it scopes it down to a single table. And that table is called my contacts table. So this is a really tight policy that doesn't affect other resources and other applications in your environment. So now our next principle is defense in depth. So this principle states that you should have defensive measures at every single point in your application. And back a few years ago, we were building large monolith applications. But today, most of our applications look more and more like this. So we have a lot of different components, different microservices, and every single piece needs to be protected using a different type of security mechanism. So if we take a look at this, defense in depth says, okay, if I'm building a web app, I probably want to enable a service called AWS Web Application Firewall, or WAF, to protect my front end. Right? I want to protect it from DDoS and all the different types of attacks that can come from the web. Once my user has made it into my web application, you should also look for building authentication on top of your application. And you can do this pretty easily with AWS Cognito. It's a security service that helps you integrate authentication and security on top of your web applications. Once you're into your application, actually performing compute on Lambda, IAM takes over. So IAM is at the core of Lambda security. Everything that your Lambda function can do and cannot do is defined in an IAM policy, an IAM resource that you attach to your Lambda function. At the very back end, all of your data needs to be protected. So what we want to do is potentially use AWS KMS, which is the key management service, to encrypt, decrypt, and lock down all of our sensitive data. So moving on to our third security principle, and this one's kind of cool. This one is clean code. So when we mean clean code, that means never store any secrets hard-coded in your application. Right, so don't store database secrets, don't store IAM keys and credentials in your application code. It's bad for security, but it's also bad for CI/CD, because if you have to change those pieces of information, you effectively have to deploy a new version of your code. So in the IAM world, instead of storing hard-coded credentials, make assume role calls to get temporary credentials. And those credentials only last for a certain amount of time. So if you lose those credentials, they effectively go away and no longer work. You should always store your database usernames and passwords in an external file, encrypted in an environment variable, or take advantage of the AWS Secrets Manager. So the Secrets Manager is responsible for storing, rotating, encrypting, and delivering secrets to your services that integrate with it. So you no longer have to worry about all those details about protecting your sensitive secrets. Now the second piece here is that we want to keep, as developers, we want to keep our code as simple as possible. So Lambda functions should be as small as possible, and we want to group them based on the type of access they have. So let's take a look at an example of how that works in the real world. On the left here, we have a Lambda function that's basically a monolith, right? This Lambda function is intended to execute for any API call made to it. And this Lambda function is going to need permissions to write to two tables, customers and orders, and also talk to an SQS queue. So this Lambda function is going to need a pretty verbose set of IAM statements in order to talk to this environment. What we really should be doing is splitting this Lambda function into three. So on the right side, each Lambda function has a single set of responsibilities. And those responsibilities are simply to talk to the resource that it cares about, and maybe add or delete items within those tables. And then that bottom one is only working with an SQS queue. So this allows us to scale better. It allows us to make our security policies a lot more granular. And if we lose control of one of these functions, it doesn't affect anything happening in our other functions. So now, when we kind of covered the basics, let's move into some of the security patterns that you should be aware of in the serverless world. So our first pattern is web application vulnerabilities. So there are all different types of vulnerabilities that developers have to protect against. And when we're building our serverless applications, we typically don't have to worry about infrastructure security and hardware security and file system security. But we still have to worry about all the same security details that application developers have to protect against and defend against on the web. So an example of these, on the web, you have to worry about DDoS or cross-site scripting, right? And then when you actually get into your REST APIs, most of us are making application calls, REST calls against APIs using JavaScript these days. Right? A lot of your single-page web apps using React.js or Angular, all of those are making cross-domain calls. So we need to understand and have a good policy for how CORS works, so cross-origin resource sharing. So allowing or denying certain domains to access your APIs securely. And then finally, when you get into Lambda, we have to worry about SQL injection. So there's a common misconception that just because you're in a Lambda managed service, that SQL injection doesn't exist. So we'll see a little bit later how SQL injection is definitely an issue and how you can defend against that, right? And then obviously, when we get into our databases, data loss is always a problem. So we talked about using KMS to protect our keys and making sure all of our data is encrypted and all the sensitive information isn't accessible to any standard user, right? So the good news is that out of the box, AWS has a lot of services that can help you with this. One of the really great services is the application firewall, so WAF. Application firewall gives you the ability to control what traffic to allow or deny into your application. And the way you do that is creating an ACL or an ACL. And then an ACL can have as many rules as you want on it. So your rules effectively control what traffic you're going to allow or deny into your system. So let's kind of look at how that works. So in this example, I've created a single ACL. It's called demo ACL, and I have 4 rules set on it. So all 4 of these rules have to match and allow before my user is allowed to reach my application. So the first rule is titled US only. So I'm going to allow requests that are originating from a US IP address only, because maybe I know my application is only meant for US-based users. Right? This could be any geography, but in this example, it's just US-based users. I've added a second rule that says, don't allow cross-site scripting. So WAF has a built-in ability to inspect all requests and determine whether or not there's cross-site scripting and other security vulnerabilities in it. But I'm specifically saying I want to block all requests that have cross-site scripting detected by the WAF service. And then the next rule that I've set up is that I don't want to allow any requests that are bigger than 1 kilobyte in size, because I know my application doesn't work with requests that are that large. Right? So, obviously this one's going to be customizable depending on what your application is doing, but you can customize and have WAF inspect the size of the payload and then block payloads that are too large, because that's also a security problem, right? And then finally, another out-of-the-box thing that WAF can inspect is for SQL injection. So it can look for common SQL injection patterns and then automatically block those requests that are flowing to your web application. And on the right over here are all the different other things that WAF can inspect for out of the box. So our second pattern is web authentication. So most applications on the web today have some portion of their application that needs to be secure. It needs to perform login, authentication, and authorization. So there are many different options that you can choose from. You can use IAM authentication, you can use Cognito, or you can use OpenID Connect. And OpenID Connect is probably the most common because it's the most cross-platform these days. So we're going to talk a little bit about OpenID Connect and focus in on how you should use OpenID Connect securely. So OpenID Connect is essentially works when a user logs into an identity provider. And that identity provider, if it's OpenID Connect compatible, will return a JWT token, so a JSON web token. And you as an application developer are responsible for grabbing that token, saving that token, and then passing it along downstream to any application you want the user to authenticate against. So most developers tend to store this JSON web token, or the JWT, inside a secure cookie, or also potentially inside your browser local storage, right? Encrypt them and put them in a secure place. So let's take a really quick look at what a JSON web token looks like. So JWT is a self-contained, stateless way to transmit identity information. And it's always made up of 3 pieces of information, base 64 encoded. Right? The first piece is the header, and the header just defines the algorithm that is used to sign this token. So very basic information here. The main part of this token is going to be the payload, or the second part. So a payload contains all the claims, all of the expiration data, and all the information about who this user is and what kind of access that person has. And the final piece is just the signature of the token. So when I have this token as a user, I'm responsible for delivering that token to any downstream application that needs to access, that I want to access. So when I deliver that token to a downstream application, that application as a server is responsible for parsing out the token and verifying all of the claims on it, including the expiration date and whether or not this token is actually valid. So this is a typical OpenID Connect workflow. So one of the great things is that you can use this type of workflow integrated out of the box with Amazon's API Gateway service. So when you perform a login against Amazon API Gateway will automatically construct a context object. So that context object can be accessed when you're doing your transforms inside API Gateway. So the $ context object will get automatically populated with all of the identity information that API Gateway received. So some of the examples could be the account who's executing this API, the IP address, the username, the AWS organization that's trying to perform this API call, and a lot of different other sensitive information. So as a downstream application, my Lambda function can actually check this context object and make sure that it has the things that it needs in order for my application to return the correct details. So you can perform really fine-grained access all the way down to your compute layer with this kind of setup here. So Let's move on to the next section, which is going to be a discussion on some of the tips and best practices that you can use today in your applications. So here is a template of an IAM policy. How many of you have written an IAM policy before? Probably everyone, right? Awesome. So IAM, as you know, is at the core of serverless security. It controls everything a Lambda function can do, and pretty much it also controls who can invoke your APIs, who can access your DynamoDB tables, and all of your resources. So here is a really basic IAM policy. The structure is very simple. IAM policies always have an effect, either allow or deny, then you have some kind of action. Right? This action can be a list of API calls that you want to allow or deny. And at the very bottom, you have a resource. So a resource is the AWS resource that you're providing permissions to. So let's take a look at some special IAM tips that you may or may not be aware of. The first one is called IAM conditions. So IAM conditions is a special attribute on IAM policies that evaluate dynamically at runtime. So when a user executes and signs their AWS request, we'll run this conditions attribute dynamically at runtime and then perform these conditions evaluations. So here's an example where I'm using the AWS source IP as a condition. So this IAM policy says I want to allow two S3 API calls, list bucket and get bucket, but only if the condition matches. And that condition is the source IP has to originate from this IP block. And I would probably put this kind of permission in if I know that I have admin users that should only be running from a corporate network. Right? I probably don't want to allow random users from other IP blocks to execute these type of calls. So we have a lot of different conditions attributes that you can use, and here's a good example of some of the more complex ones that are out of the box but very powerful. So an example is current time. So if you know that your admins only work during a specific time, you probably don't want to allow API calls to be made outside of a time. So you can check current time to see if it's within a certain window. Another really great one to look at is secure transport. So you can enforce that all calls made to your APIs come over HTTPS. So you can say, I don't want to allow any plain text HTTP calls to invoke my API. Another one here is user agent, but you can check to see if a user is coming from a browser or from a mobile application. Be careful with this one because user agents, as you know, can be easily tampered with and changed based right there in your request. Another great one is the AWS principal org ID. Has anybody used this tag before, principal org ID? Cool, we got about a handful. So the principal org ID is interesting. It says that whatever organization I belong to, I have to have this specific organization in my hierarchy chain, my count chain, in order to be able to execute this call. So if you're using AWS orgs to manage one parent account with multiple children, and you want to have all of your permissions roll up to a single AWS account, you can use this conditions attribute to help you do that. So let's take a look at something that's a little more complex. With this conditions block, I'm providing a single allow statement that says AWS Lambda invoke function. So I'm going to allow a user to invoke a specific function that's called out on the resource line. But I have this invocation has to match two resource conditions at runtime. So the first one is that principal org ID. It has to originate from my specific organization. And number two, I have to come across using HTTPS. If both of these conditions don't match, IAM will automatically decline and reject this request, even if the user has other permissions to do it. So who's written a Lambda function before? Great, there's a lot of you guys, awesome. So Lambda functions, the permissions model has two models. The first model is the execution role. So Lambda functions always have an execution role that's attached to that function. And that role defines everything a Lambda function is allowed to do or not allowed to do. So let's take a look at an example of that policy. So here's a policy, an execution policy that's attached to a Lambda function, and it provides at the top here a single DynamoDB put item permission to a single table called test. So if I were to attach this function, this IAM policy to my Lambda function, my Lambda function can only do this API call. Even if I had application code written to talk to other tables or S3 or other AWS resources, this is the only permission that my Lambda function is allowed to execute. At the bottom here is a trust policy. So this is the second piece of my execution role. We have to have a trust policy on your role that allows the Lambda service itself to assume the role and execute the function on your behalf. So without this role, won't be able to execute your Lambda function. Now the second piece of the Lambda security model is a resource policy. So a resource policy is kind of like the opposite of an execution role. Now a resource policy says who is allowed to invoke my Lambda function, which principal, which user, which account. Because you can share Lambda functions across accounts. You can make them public if you wanted to. So let's take a look at that real quick. Here's an example of a resource policy that I've added to my Lambda function. And this resource policy, it's a little bit long, but if you look in the statement section here, it provides a single allow statement to a service called API Gateway, right? And the API Gateway has one permission on it, and the action is Lambda invoke function. So essentially what I'm doing is allowing my API Gateway service to invoke my Lambda function. Because what I want to do is build a microservice that's hosted on API Gateway, and the compute behind the scenes is driven by my Lambda function. So using this kind of policy, resource policy, you can easily allow other services or users to invoke your Lambda functions, still subject to that execution role that we looked at earlier. So how many of you have used IAM Pass Role before? So this one's a little more complex. IAM Pass Role basically defines a permission that allows a user to assign an IAM policy to any resource. So if you're an administrator, you probably don't want to allow developers to assign any random IAM policy to a Lambda function, right? So you want to only allow specific permissions and specific policies to be assigned to Lambda functions. So you don't want to allow, wildcard permission to be set on a Lambda function that goes into production. Instead, you would use the IAM Pass Role permission to allow a specific user to pass roles or assign roles to specific resources in AWS. So here is an example where I'm allowing 2 roles to be assigned to any Lambda function. So first one, the role is called read from context table. The second one's a little more complex because I'm allowing any role that starts with Lambda and then dash wildcard. So any role that has a name that begins with Lambda dash, my user can assign. So if you're building a security model of managing applications, it's a really great idea to create a naming convention for your roles and then use this kind of strategy to determine who can assign which roles to which Lambda functions or to which accounts, right? All right, so we talked about using IAM to secure your applications. We talked about using Pass Role to secure who can assign those IAM roles to specific resources. Now let's talk about how to access databases securely. This should be pretty familiar to anyone who's written a SQL statement before or command. This specifically is written in Node.js, but the code is pretty similar for Java or Python, right? Typical database connection strings always have a username and a password. And this is an example of a MySQL connection string. Other databases are either more or less complex, right? In Node.js, the easiest way to connect to a database is to specify the port, specify the host, and specify the username and password. If you put this into your application code, it becomes hard-coded, and we talked about that being hard to manage and also insecure. So there are better ways to do this, and here's a list of how you should evaluate how to access secure database credentials. So number one, we can hard code them. We all know that's bad security practice, so don't do that. Number two is Lambda functions support environment variables. So environment variables essentially aren't pieces of your code. They're injected into your application at runtime. And Lambda environment variables are integrated with KMS out of the box, so you can encrypt and protect your secrets. You can even change those secrets easily. So it's really easy to manage your secrets that way. Number 3, 2 and 3 are kind of very similar in terms of security posture. You could externalize your database secrets, put them in a config file, encrypt and decrypt them when you need to. Number 4, is to externalize into another data source that's not hard-coded. So I would take a look at DynamoDB as a really great environment for storing configuration for your Lambda functions. DynamoDB supports encryption at rest, and you can also encrypt these variables or these strings as you insert them into your table. Secrets Manager is a fairly new service. It has all of these capabilities built out of the box, including automatic secret rotation. So if you have corporate policies that say secrets have to be rotated every 30, 60 days, Secrets Manager can help you do that. If you're not aware, you can use IAM authentication against some flavors of RDS. So what that means is you never define hard-coded users in your databases. You simply have IAM users that are part of AWS, and you use those users to access your database environments. So definitely take a look at how that works. And also, I would encourage you to just enable SSL only across your databases. Only allow secure connections to your RDS instances. And it really, there's no reason not to do it. I think your code has to change a little bit. You have to include a certificate file that we use to negotiate the secure channel. Other than that, it's pretty straightforward for most programming languages. Okay, so we talked about defending your applications, but auditing your applications is equally as important. So AWS Config is a service that allows you to automatically track a timeline of changes, configuration changes against any resource in your account. So here's an example where I've deployed an API Gateway resource, and API Gateway is emitting config changes to AWS Config. So as we can see here, on May 17th at 1:41 p.m., I made a configuration change on API Gateway. And this configuration change specifically was recorded by config. And it's telling me that I have disabled the API throttling on API Gateway. And while that in itself is not a security issue, it's probably an issue that somebody needs to look at, because I probably don't want to disable throttling. I need to have some kind of throttling for my API calls. So config can automatically track these changes and then trigger rules that you can remediate. So these rules can be simply just notifying someone, but you could also trigger a Lambda function that executes and then immediately puts this configuration back in place. So it's good for auditing and remediation. So if we look at a second example here, maybe 2 minutes later at 1:43, I now went and disabled logging. So this is probably more of a security issue, and because I disabled logging, config is tracking these changes and can automatically notify somebody, an administrator, or perform some kind of action against this change. So I highly encourage you to take a look at config, use it to help meet your auditing and compliance needs across your corporate environments. All right, so this is the common vulnerabilities section. So let's take a look at some of these, but before we start, please do not execute any of these examples on any system that you do not own. So this is kind of the fun part, but please only run these on test environments that you own, right? So SQL injection. Has anybody had the experience of working with a SQL injection? Cool. Is that fun? Probably not. So SQL injection is actually one of the top risks as identified by OWASP for web applications, one of the top 10. So a SQL injection is essentially when an attacker adds extra SQL to your code that your code executes without you knowing it. So here's an example where I have a select statement. So select star from contacts, where email equals some value, right? abc@domain.com. Typically, my web app will construct, my server-side code will construct the SQL query and accept that email address as the parameter, right? Does that make sense? So once this happens, an attacker could be smart, and instead of passing in a valid email, they could pass in something like this: abc@domain.com, tick mark, semicolon, drop table, contacts, dash dash. So there's two things to look at here. The semicolon in a SQL statement says end the SQL statement. A dash dash says comment out anything behind it. So when this gets assembled together by my code, this is what it looks like. Select star from contacts where email equals this large string. So if you read this carefully, this is actually two SQL statements. First one is select all this information, give me every single contact or all columns from this contact where this contact has this email address, but also just drop this table. So if you don't have your permissions set up properly and you're allowing this to happen, you've just given all information about this contact to your attacker and lost your entire table. So definitely keep this in mind when you're building your applications, and we'll show you how to protect against that. But here's another example. Also SQL injection. Select star from employees where the person's first name is some name, right? Doesn't matter, George, Alice. Instead, if I as an attacker enter this as a string, what do you think happens? Tick mark or 1 equals 1. And I've assembled the tick marks in a very strategic order to make sure that it is a valid SQL statement. So read that carefully. And this is what it assembles to. Select star from employees where first name equals tick tick, so just empty string, or 1 equals 1. So what is 1 equals 1? It's just true, right? So when a SQL statement executes like this, when something equals something or true, SQL will just return every single record that matches true. So that's going to be every record in the table. So using this kind of attack, an attacker can grab every single piece of information from my table, even if I have fine-grained role-based access turned on, right, in my application code. So here's an example where this works in a Lambda function. So remember, just because we're in serverless does not protect us from this kind of attack. So as you know, Lambda functions always require you to have a single parameter. That's the event parameter, and that event parameter contains information about why you're executing your Lambda function. And here is a sample event parameter. It's got a couple attributes on it, but I've defined an attribute first name that has that attack string on it. And down below is standard Java code that's going to execute a query, same query we saw earlier, select star from employees where first name equals the input. When that happens, this is the output that I get from my Lambda function. So I'm getting every single record from the table, even though it should have just been any employees with a first name match of the parameter. So keep in mind that the same attacks that can occur in your traditional server-based environment can occur in Lambda today. So what that means is that input can come from anywhere. That input could be an S3 file that you've just read in. It could be an API call that was invoked from API gateway. So what we want to do when you're building your applications, always use prepared or precompiled SQL statements. And this is an example written in Java, but the same concept is available for pretty much any programming language out there. The idea is that you want to precompile your SQL statements so that the server knows it's going to expect one single input and only that. And it won't execute any other SQL that isn't part of this compilation. So here we're doing a prepared statement. We're going to set a single variable as defined with a question mark, and then we're going to set that as a variable. So once you have this set up, any attacker who tries to do the same thing is going to fail when they try to execute that statement. All right, so the second most common risk to web apps today is cross-site scripting, or sometimes called XSS. So cross-site scripting is when an attacker injects JavaScript into a website that a different user's browser executes, right? So as an attacker, I want to put some kind of malicious JavaScript code into the application that gets read out and executed by one of you. So here is a standard HTML image tag, right? We've probably written hundreds of these, right? So image source equals image.png. So this is very standard HTML. It's going to load an image. This actually works. You can say image source equals # on mouse over equals JavaScript :alert document.cookie. So our browsers will actually execute this call and then return the cookie that's currently on your domain, because your browser allows you to read your own cookie, right, in the current session and domain you're in. So you can use something similar to this to perform an attack. This works as well. If I ran a script block in my HTML code that runs some JavaScript to create a new image on the fly. So new image.source equals, instead of putting a hard-coded file name, I put in an HTTP address. So here it's just HTTP 111.222.3.4, right? This is going to tell your browser to make a GET request against the script that's right there. So this is a server that I, as the attacker, own. Your browser has executed this and now just sent your cookie to me. So when I get your cookie, I can take your cookie and that JWT token that might be in there and log into the application as one of you. So let's take a look at how this works. Here's a Firebug trace of exactly what just happened. On the left here, my browser has made a HTTP request. I can see that it's insecure. But as an application user, right, one of your customers, this isn't going to be visible to them. They're not going to have Firebug or Inspector open. They're not going to see anything in their browser. They're just going to see that your code worked fine. On the right here, we can see that my browser made that HTTP call all the way out to, that IP address, and that I actually don't own that IP address. So it hit that stealyourinfo.php script and just sent my cookie with a name of my cookie has been stolen over to that address. So this is super simple code that can easily be put into any browser and executed by put in by an attacker and executed by any browser. So the major concept to keep in mind here is that your application threat model is still the same. When you're building applications in serverless, it doesn't mean that you no longer have to protect yourself against these types of vulnerabilities. And the only thing that changes is some of your approaches and how you protect yourself and some of the tools that you might use. So we looked at config for auditing, right? We looked at IAM protect for doing authorization and authentication. So in summary, take advantage of all of the AWS security services out of the box. Make sure you're using WAF, right? Enable it on CloudFront, turn it on your API gateway resources. Make sure you're using AWS config to audit your environments. Even if you're not remediating, you should turn it on to audit and track that timeline of changes. Because it could be useful when you have a bug. You could go back and determine who made the change and when that change was made. Make sure you use IAM properly, right? Scope your policies. Don't allow wildcards in your policies. You should have some kind of automatic code inspection on your policies that detects wildcards. And those are generally red flags for your security team. And most importantly, remember that HTTPS is not secure, right? It's a secure channel for delivering information, but as we just saw, HTTPS is not secure just because you have it turned on, right? Your application still needs to validate user input. It needs to encode all of that JavaScript and into other formats and not accept those directly out of the box. You should always escape HTML in any one of your inputs. And anyone who's working with SQL should look at SQL injection and always use precompiled SQL. Right? Don't use dynamic SQL that you construct on the fly. Right? We do that a lot. I've done it before because it's easy as a developer to get started. But definitely take a code review and inspect and see how much of your application talks to a relational data source and see if you have any of these dynamic SQL statements written in your code. And finally, understand JWT. Right? JWT is one of the most common ways of authorizing access to third-party services. It's really scalable because it's stateless, but keep in mind that JWT needs to be authenticated. You have to validate the signature, and you have to make sure that it's not expired. Like, that's a big one. JWT tokens always have an expiration date, and you should never accept a token that has lost the expiration date. that's basically it. Thank you so much for attending, and please reach out to us if you have any questions. And I would encourage you to please submit your feedback in our mobile app. It really helps us shape the next sessions and the next year of this conference. Thank you.